This was like this was like predator versus prey. This was always like an alligator, the other one was a snake. I always thought snake was
All right, so any questions first on the homework before we just kind of run through all of it? How was Dijkstra's algorithm? Everyone got that written up? Cool.
I think it was, it's similar to number 2, but it was the one that was directed. I think it's like 4 or 3.
Draw a directed graph for the following adjacency matrix. Oh, okay. Let's do that one.
I'm not sure if I did that right.
That's the thing, I may have gotten the arrows backwards.
Well, it's all relative, right? It's isomorphic.
But if you have the same graph but with the arrows going the other way, is that isomorphic?
I don't know. Let's find out. So here's a adjacency matrix, and we're told this is directed, which we can tell because it's not symmetric, right? The row and column versus column and row aren't the same. So I'm just going to label these, and the labels are arbitrary. And there's usually a better place to put your vertices to make the graph look pretty, but there's no way to know that ahead of time. Well, there's no way I know it ahead of time. So I'm going to say that this is from and to, and then we'll draw it the other way and see what happens. So we're going from A to A, and that's just a loop to itself, A to B, and A to C, and then B to C, and then C goes to A, and C goes to C, and then D goes to A, B, and C. So A, and B, and C. So there's a graph corresponding to that. Now let's just try it in the other direction. So let's suppose this is from on top and to on bottom. So A still goes to A, and it also goes to C and D. B will go to A, and B goes to D. C goes everywhere. This is looking like it's going to be different. And then D goes nowhere. So, how similar are these?
It's the same for everything except the arrows are basically the opposite direction.
Yeah, so we've swapped in degree with out degree, right? So this has an in degree of 3. There should be a node up here with an out degree of 3. That would be D. B has an in degree of 2 and an out degree of 1. B has an in degree of 1 and an out degree of 2. Right, so it feels from that like we've just swapped in degree and out degree. So is that an isomorphism? We didn't really just define isomorphism for directed graphs. Other than to say we can rename the vertices and get the same graph. And so, yeah, they're not isomorphic, but they are somehow pretty closely related. So if you did this instead of that, it will look different, but you still get credit.
Yeah, there's no standard for that.
I don't think there's a standard.
Okay.
Yeah, you'd have to define it when you set up your adjacency matrix. so let's look at question 1. Thanks. Yeah, if you came in late, bring your homework up, please. Alright, so this one wants an adjacency list, an adjacency matrix, and an incidence matrix for the following. So there's our graph. So an adjacency list, remember you list each vertex and you show the nodes that are adjacent to it. So it might be something like A is adjacent to B and D. B is adjacent to A, D, and E. C is adjacent to D and E. D is adjacent to lots of stuff. And E is just B and C. And I don't mind if you use commas or spaces or whatever. It's just listing the information. So that's just showing if we want to know what's adjacent to a vertex, we can go into that adjacency list and just pull out the vertices one by one, which is useful for some algorithms. An adjacency matrix, well, we just reversed one. So it's undirected, so A, we just need B and D, and we're going to have zeros everywhere else. And since it's undirected, this is going to be symmetric, right? Element row, comma, column will match element column, comma, row. So we can also fill in A, B, D like that. And then B is connected to A, D, and E. So we can fill in the second row and column. C is connected to D and E. So we can fill those in. D is connected to A, B, C only. And then E is connected to B, C only. So there's an adjacency matrix. And then the incidence matrix, it depends where you want to put your edges. Do you want them to go horizontally or vertically? It'll give you a transposed matrix, but it's the same information. So let's just put edges down here. And then vertices horizontally. And you just list which edges are incident to which vertices. So A, E1 and E2 are incident. B, we have E2, 3, and 5. C is 4 and 6. D is 1, 3, and 4. And E is 5 and 6. So those are the 3 ways we talked about representing graphs. All right, undirected graph for the following. And this is easier than the following problem that we already did. So we'll switch up the vertex names just for fun. So there's X, Y, Z. So X is connected to Y, Y is connected to X and Z is connected to Y. It's a triangle. Ooh. All right, isomorphisms of graphs. So 2 graphs. So you're asked to sketch them, label the vertices from the first ABC and the second XYZ, and then say whether or not they're isomorphic. And if they are, show a mapping. If they're not, convince me why they're not isomorphic. So we can go ABC, XYZ. Did I do XYZ or WXY? XYZ, good. All right, so what's this first graph look like? A is connected to A and C. B is connected to B and C is connected to A and B. And the second one, X is connected to itself and Y. Y is connected to X and Z is connected to Y and itself. And those sure look isomorphic, right? So to prove an isomorphism, we need a mapping from this set of vertices to that set of vertices. So yeah, that sounds good. All right, so where do you want to take A? X and B, Z and C, Y, right? And that's a perfectly good mapping. We always use Greek letters for isomorphisms, I don't know why. So there's a phi mapping from those vertices to those vertices.
Could we have used the arrows?
Yeah, you could use arrows too. All right, so what's happening when we're applying this mapping from vertices to vertices? What happens when we replace vertex B with vertex, or when we map vertex B to vertex Z? We're saying that this row corresponds to this row, and that this column corresponds to this column. We're really just swapping rows and columns, right? If we take this matrix here, and we take the third row and the second row and swap those, right, so we've swapped these. And then we also swap the second and third columns. We get exactly our original matrix. Right, so that's what the effect of this isomorphic mapping is doing. It's just interchanging rows and columns. But if you change second column with third column, you've also got to change second row with third row, right? Because you got to do both sides. All right, so consider the following graph. For the following ordered list of vertices, indicate whether it's a path. If it's a path, what's its length? Is it an Euler path, and is it a circuit? So A, B, E, C, B. So A over to B, we can get there. Over to E, we can get there. Over to C, we can get there. And back to B, that is a path, right? Because we're following these edges in the direction indicated. And the length looks like 1, 2, 3, 4. 4 edges. There's really no choice because we got 5 vertices. Is it an Euler path? Right, so we did not hit all of the vertices. So it's not an Euler path through the graph. And is it a circuit? No, because it ends at B and it started at A.
I thought Euler was the edge one. Hit all the edges.
Yes, yes. Hamilton is vertices. Yeah, so we didn't hit all the edges. Thanks. So it's not an Euler path. All right, second one, A goes to B, goes back to A, goes down to D, and goes back to A. So that's a path, and its length is 4 edges. It's still not an Euler path because we didn't hit these edges. But it is a circuit. It started at A and it ended at A. It's actually comprised of two circuits. A goes to B, goes to D, goes to E, goes to A, and there's a few problems there. It's definitely not a path because we can't get from B to D. There's no edge connecting those. So it's not a path, has no length, it's not an Euler path, it's not a circuit. And then A to B to E to C to B to D to A, again, B to D is not a path. Right, so that's nothing. All right, does the following graph contain an Euler path? So what did you find for this?
Yeah. Probably.
Yeah? So what was your path?
I think I had to start at A and end at D.
Okay, so you came out here, and we could come down like this, and we could go bang, bang, and come up here, and come down here, and then go up to B and down to D.
Yeah, that was good.
So that would work. And there's probably other options too. All right, is there a Hamilton circuit for this graph?
Yeah. Oh, I said no.
It's either yes or no.
Yeah.
Yes? Okay, so where do you start?
You start at D, go to A, go to C, go to B, go to E, go to F.
Yeah, but let's talk about a circuit. You have to end at A, or end where you
Oh.
start.
Oh.
Yeah, you have to end where you start,
Oh.
and you're going to have to hit E twice.
I misread the instructions.
Okay.
So, for the question before it, though, there was another part to it.
Oh, to contain an Euler circuit. So, did anybody find an Euler circuit?
I said no because it's kind of odd.
Yeah, I don't think there's an Euler circuit, and the even odd thing is a little weird with directed graphs.
Oh, I didn't even
But-
get that.
But yeah, basically, if it's got an odd, right, you're going to have to start or end there. It doesn't guarantee that you have a circuit or a path just because there's odd numbers. But
But if it's not, if it can't be, if it can't have a circuit, if it's not directed, being directed isn't going to help.
right.
It isn't going to make a set possible.
Right. Yeah. So we only have one odd vertex. So, well, no. Is that true?
D is 5, I think.
D is 5. Right.
There is two odd ones. But we'd have to end at D or end.
We'd have to
at
end at D. Right. All right. So yeah, this one won't have a Hamilton circuit because
Passing through C and E are.
yeah, if we start at F, we're not going to be able to get back to F, right? Because we'll go through there, and if we don't start at F, right? Whenever we visit F, we can't get back, basically, right? The only way to F is through E, and once we're there, we can't come back to E. So there's no circuit. All right, then Dijkstra's algorithm, you did on the board beautifully yesterday. Cool. So any other questions on the graph stuff? So I'd like to talk about two other graph-related things. Thanks. So, spanning trees. So if we have a graph, we'd like to find a tree that contains every vertex, but clearly not every edge. I don't know what I'm making here. Just kind of going crazy. All right, that's enough. So there's a graph, right? It's definitely not a tree. Remember, trees can't contain cycles. And if we start at A, we can go to C, B, and come back to A. That makes it not a tree right there. But it is a graph. But within a connected graph, there's always at least one tree, which will be a subgraph of your original graph and will contain all the vertices. And such a tree is called a spanning tree. And sometimes it's useful to construct spanning trees from a graph. And it's really easy to construct a spanning tree, right? You basically just start removing any edges that give you cycles. So I can get rid of this edge. And I've got a cycle here, so I don't know, I'll get rid of this edge. And I've got a cycle between D and F, so let's get rid of that. And let's get rid of this one. And there's a graph, so let's cycle, so let's get rid of that. And we'll get rid of this. And here's another cycle, so I'm going to get rid of that big long edge. And we still have a cycle here. I'll get rid of that big long edge. And do we have any cycles left?
One around the edge.
There is one around the edge. All right, how should we get rid of that? Let's just kill off that. All right, so let's see what we have left. We have A, B, there's C, there's H, there's D, E,
There's
F. Oh yeah, okay, so we'll kill that off since I haven't drawn it yet. And then H goes to I, and F goes to G, and we've got another cycle, so we'll kill off that edge. And I think we're good now, A, B, C, D, E, F, G, H, I, and that's a tree. So you can always do this, and it's really easy. You're basically just eliminating the things that stop it from being a tree. So just wipe out all the cycles. Alternatively, you can do this constructively. You can start with a single vertex and then add any vertex that isn't already part of the tree. So we could start with just the single vertex A, and B is not a part of the tree, so we can add an edge between A and B. And C is not a part of the tree, so we can add an edge from A to C, and then find an edge that connects D to the tree you have so far, and keep building up like that, right? But you only add things that aren't already reachable from the tree, and that's going to prevent building cycles in the process. So making a straight spanning tree is pretty straightforward, but it gets more challenging when you have weights. This isn't a critical example, it's just stuff. What?
I was like, now that you've drawn all this,
Yeah, now I gotta come up with interesting looking weights. All right, so we have a weighted graph, and we'd like to find a minimal spanning tree. Okay, so we want to find minimal spanning tree.
You're just going to do like a bunch of divergence algorithms?
It's way easier than that. So minimal meaning lowest total sum of weights. So what's an application here? You're wiring up a town, right? Each vertex is a house, and each edge is a pathway along which you can run wires from one house to another. And you don't need multiple connections from one house to another. You're going to have one house that's supplying electricity, and it's going to send electricity down the wires to every possible house that's connected to it. And you can go through a house to get to another house. So if you can find a spanning tree, that's going to be the fewest number of edges, and if it's a minimal spanning tree, it's going to take the least amount of wire, assuming these numbers are the distance if you take that path to run your connection. So a minimal spanning tree would tell us an optimal way to connect all of these vertices together with the lowest total weight. And it turns out a greedy algorithm works great here. So I'll label these. And this is something called Prim's algorithm. So how does Prim's algorithm work? You can start with any vertex you want, because every vertex is going to be a part of your minimal spanning tree, right? So we can start with any vertex that we like. Let's just start with A, because it's alphabetical. And we add the shortest edge connected to A that does not create a cycle. Okay, so connected to A, we have edges of length 1, 4, and 5. We're going to choose this edge of length 1, which brings us to C. And now we find the shortest edge connected to this tree that does not create a cycle. Well, we've got 5, we've got 2, we've got 2, we've got 1, we've got 2. So 1's going to be the shortest edge. So let's put in our edge of length 1 over to G, and you just keep going. Okay, it's greedy in the sense that at each point we're doing something that locally gets us to our global solution. Globally, we want the smallest total weight, so at each step we're adding an edge that gives us the lowest total weight so far. That's classic greedy algorithm. All right, I should be filling these in up here so we can find our vertices more easily. So what's the lowest weight edge from here? Or a lowest weight edge, and it may not be unique. If it's not unique, you can take whichever one you like. All right, so we include G to I and I to F.
So is this a tree that has to have 2 branches, or it can have any number?
It can have any number. It's not a binary tree in general. All right, so now that's our collection of vertices and edges. So let's go on to some 2s. So which 2 should we include? F2D. I like it. So we got this. Now we're not going to include D to C because that's going to give us a cycle, right? But are there any other edges of length 2 connected to this tree?
C to B works.
Sure, C to B.
C to or I to H.
I to H. All right.
But now we have
Oh, we missed a B to E. But we haven't done anything else with E, so no harm done.
that's all.
C, E, F, G, H, I. We've got all our vertices, so so we're done. And there's a minimal spanning tree.
This is like, I don't know. This feels interesting.
Yeah.
This does seem like it's counterintuitive, but it does look like it works out.
Yeah. And you can prove all of these algorithms with varying degrees of difficulty. We're not going to do that in here, but in a advanced data structures course, right, you would spend some time proving the correctness of these things. And Prim's algorithm is not too bad to convince yourself that it actually works, right? If Yeah, maybe you can recurse on the number of edges.
Oh, it's like you are definitely going from each point to another point in reduced of weights.
Mm-hmm.
That's like guaranteed, and if you do that, then it must be that the tree is also reduced.
Yeah. I mean, the counterpoint danger is that if we hadn't taken this edge of length 1, we might have gone to another edge which would have had shorter distances to some other node.
Right, this
Right.
is for finding the shortest path.
But it's not finding the shortest path, it's finding the shortest sum
Yeah.
of weights. So that's Prim's algorithm. And a lot of this depends on cycle detection. The cycle detection is an interesting problem with a graph, right? I mean, you discovered this sometime deleting nodes from binary trees. You inadvertently create a cycle, and when you try to traverse, you just keep chasing yourself forever. So how can you detect a cycle in code?
If you have a linked list, then you can have 2 markers
Mm-hmm.
and increment them by different amounts
Mm-hmm.
over and over again. And if they ever hit the same place,
Okay.
then there's a cycle.
Cool. That's a nice
That would
algorithm.
work, actually. I
Yeah.
was just thinking, like, if you wanted to do more memory less time, you could just remember every place you've been and
Yeah.
see if you go there again.
Yeah, so you can augment these nodes by a flag, right? And each time you hit a node, mark it as being visited. And now do your tree traversal, right? Pretending this is a tree. And if you come across a node you've already visited, you know you got a cycle.
What's more, if you traverse to a different node, depending on condition, you can store what was previously the condition for traversing at each node, and then see if you come back to that node, you have the same condition again, or you have a different one.
Right, right. Cool. So these are all good things to code up.
There are a lot of applications to that.
There's what?
There's a lot of applications. to that.
Yeah, definitely. This stuff comes up a lot in like networking, when you're trying to deliver network traffic, right? You're usually going through customers along the way, and minimizing that is important energy-wise. All right, well, want to talk about the final? Okay.
Wait, do spading trees have like a method for directed graphs? Is that a thing that can exist?
I think that changes the equation.
Because that might change a lot, but it also might not change anything.
Yeah. If it's directed, right, you have to follow the directions.
Well, I guess there might be 2 nodes that are, you can't go from one to the other in just a possible way. So that might be-
Yeah. I'm not sure if the greedy approach works for a directed. These
Well,
are,
tree exist for a directed graph all the time, but that may not be necessary. That's true.
yeah, these things are annoyingly deceptive, right? Things like negative weights in Dijkstra's algorithm suddenly breaks, right? Adding direction changes the equation sometimes. Graph theory is one of those subjects in general that can be intriguing because, again, the questions are pretty small and the answers can be huge. Really basic question, how many graphs can you make with a certain number of vertices, right? And, you know, discounting isomorphisms, how many graphs can you make with 5 vertices that are fundamentally unique from one another, fundamentally different? And it's not always clear. Right, so.
They've done research
Hmm?
on this. They've already done something.
Oh yeah. Lots of stuff has been done. 5 vertices, there's 21 connected graphs.
So is there like a equation, I guess?
I don't know if there's a simple equation. Yeah, apparently there is.
I mean, what it's simple.
There you go. C to the n choose 2 minus 1 over n, sum from 1 to n minus 1 of k, n choose k times 2 to the n minus k choose 2 times the number of k combinations. Obviously. Yeah.
It's cool that the equation.
Yeah.
You can go to the end of the.
Oh,
list.
that's number of k vertex graphs, so it's a recurrence relation. Yeah.
Oh, never mind.
Yeah. Number of n vertex caterpillars. Can't have trees without caterpillars. Yeah, so this is a really wild area of mathematics and computer science. Right? There's lots of things you can ask.
Other central factor. Cool.
Yeah. And somewhere I found a nice collection of what the actual graphs were for different numbers. Oh yeah, here we go. So 5 vertices, there's all the 5 vertex graphs. This is including unconnected ones as well. Right. And someone got to name them like crickets and bulls. Yeah.
Chair.
A butterfly, which is also an hourglass. That's rude to someone.
They didn't label Xbox though.
Yeah. All right. So yeah, graph theory's a whole subject in itself. All right. So potential topics for 215 final exam. So let's just start at the beginning, right? So sets was where we started. Definition of a set, right? It's an unordered collection. It does not contain duplicates. Don't ever write the same element twice in a set. Set operations, unions, intersections, complements were the 3 main operations between 2 sets. Complements, remember, we're taking the second set away from the first set. So A complement B, or the complement of B in A. Start with A and throw away everything that's in B. And if we just want the complement of a set, that means the complement in the universe. So take everything in the universe, throw away everything that's in your set, and it's basically the complement, right? It's the stuff that's not in your set. The main sets we work with, Z is the integers, Q are the rationals, R are the reals. Sometimes we talk about N, the naturals, but I'll usually tell you if that includes 0 or not, or P for the positives, or maybe P for the primes, and so on. Subsets, so subsets, you know what a subset is, right? It's just made up of elements of the original set. Subset can include, right, a set is a subset of itself, and the empty set is always a subset of a set. And those are the uninteresting subsets. A proper subset is an interesting one. So it's more than just the set itself. The power set is a set, and it's a set that contains all the subsets. Okay, so the power set will always contain the empty set, and will always contain the set itself. But it will contain any other subset as well. And we saw a relationship between the number of elements in the set and the number of elements in the power set. Right? It's 2 to the cardinality of the original set. Cartesian products is another way to combine sets. So set A, set B, you can say A times B, and that's the set of ordered tuples where the first element comes from A, the second element comes from B. So the prototype for that is something like the Cartesian plane, that's R crossed with R. Set identities, so A union A is A union the complement of A is the universe, A intersect the complement of A is the empty set, A intersect A is A union B equals B union A. All of those things from 250 that we do with Boolean operations carry over to sets. Unions look like ors, intersections look like ands. You've figured this out by now. We have a De Morgan's theorem. We have adjacency and absorption and all these other things. And we can prove these properties algebraically using these identities, or we can do it with something like a truth table, what we call a membership table. So membership table, we consider any element as being a member of or not a member of each set, and that gives us our Boolean combinations. All right, functions, injective, surjective, bijective. What's an injective function?
1 to 1.
1 to 1, what does that mean?
Everything in the code in the range has at most one preimage.
Correct. So everything in the range has at most one preimage. It may not be the case that everything in the range is mapped to from somewhere. But if something maps to this point, there's only one thing that maps to this point. You never have two things mapping to the same point. Okay, what is surjective? Onto, meaning everything is mapped from something. Could be mapped 15 times to this one point, but every point over here gets mapped to from somewhere. Okay, so injective, everything's mapped 0 or 1 times. Surjective, everything is mapped 1 or more times. Bijective, both of those are true, meaning everything's mapped exactly once. Okay, so that's 1 to 1 and onto or bijective. And it's a 1 to 1 correspondence from here to here. And we like bijections. They work for lots of things. Requirement to be well defined is simply that every point over here maps to at most one thing. Right? We can't have a point in the domain mapping to two different things over here. That's the vertical line test from calculus.
Something map no headers?
Can it something what?
Because I thought something had mapped to something. Can something map to no things?
No, not if it's part of the domain.
Okay.
Right, so the domain is a set of things that map. So everything has to map to exactly one thing, yeah. All right, we talked about summation, so that's sigma notation going from a minimum value to a maximum value. It's like a for loop, okay? The choice of the variable we're using in that summation symbol is completely arbitrary. Again, just like a for loop. We could say for I equals 1 to 5. We could say for W equals 1 to 5. It's just a placeholder. Those bounds on the summation, the 1 and the 5, are also somewhat arbitrary. If we have a function from 1 to 5, we could rewrite it as a summation from 2 to 6. And everywhere that we use this variable, we can just subtract 1 from it in our expression. So we can change the indices more or less at will. And that's again like a for loop. You can say for I equals 0 to 5, you could say for I equals 1 to 6, and just use I minus 1 in your code. Right? That's all that's happening here. And we can do nested summations. So sum from I equals 1 to n, sum from k equals 1 to j, right, of something. And it's like nested for loops. You do this inner summation, and whatever you get from that, that's the thing that you're doing in this outer summation. That's your composite function. All right, propositional logic. What do you want to know here? Let's see, did I tell you what to expect on here? Nope. Okay. Propositional logic. So what do you want to be able to do here? So you want to know the building blocks, right? So conjunction is an and, disjunction is an or. Inference or implication, right? If P, then Q. Biconditionals, if P, then Q, and also if Q, then P. We can also say P if and only if Q, or other ways, but that's the arrows going in both directions. So what's a proposition?
With a truth.
Yeah, declarative statement with a truth value. So x plus 1 is not a proposition. Okay, if you're writing a proof and you're listing propositions, don't write x plus 1.
X plus like 1 root of 3.
yeah, you could say x plus 1 equals 3 or x plus 1 equals y plus 2. Those are propositions. It's got to be a statement with a truth value, so it's either true or false. So rules of inference, right? So things like things like the chain rule, things like if P then Q and P therefore Q. Okay, direct reasoning. We could also say if we know that this is true and P is true, then we can conclude Q. But I tend to stick to this notation. If P then Q, if Q then R, if P then R. So that's chain rule plus direct reasoning. And indirect reasoning. If P is true, Q must be true. Q is not true, therefore P cannot be true. Right? So indirect reasoning and direct reasoning, sometimes called contrapositive. So those basic mechanics, right? And being able to put these together to show more complex things by using these rules, right? Along with things like, if P then Q is the same thing as Q or not, as P or not Q, right? So this replacement. All right, so we'll start from there tomorrow. We'll talk about quantifiers, fallacies, proofs, number theory, and then the other stuff that we've been doing the second half of the course. All right, so we'll finish this up tomorrow.